You are listening to The Vocal Technologist. Spoken tech for your ears.
Imagine for a second that you decide to hire a brand new junior developer. You bring them into your company, you give them root access to your entire monolithic production code base, and then you just turn around and walk away.
Oh, man. I mean, any tech lead would have a full-on panic attack just thinking about the access logs from that scenario.
Right. You just leave them completely unsupervised to tear apart and rebuild the core architecture for an extended period. It sounds like an immediate fireable offense for whoever handed over those keys.
Oh, straight up. You would be walked out of the building.
But here's the wild part. That exact scenario is actually happening in production environments constantly. And it is working.
Yeah, which is just a massive shift in how we build software.
Exactly. So our mission for this session is to look under the hood of autonomous coding agents. We're going to explore how they are moving way beyond simple autocomplete, how massive tech companies are letting them loose to perform structural engineering, and, well, how we are frantically building guardrails so they do not break absolutely everything.
We really have to completely update our mental models here because the raw capability of these tools has shifted dramatically. Before we can figure out how to manage these agents, we need to unpack what they're actually doing when you drop them into a professional workflow.
Yeah, I am seeing all these major updates for models like OpenAI Codex and Claude Opus 4.7, and they're clearly doing heaps more than just suggesting a line of code here and there.
Oh, absolutely.
What is the actual step up in capability when we talk about these enterprise environments? Like, what are they actually doing?
The big leap is from passive suggestion to active operation. We have to stop thinking of them as supercharged typewriters. Codex, for example, is now built to physically operate a computer alongside a user. It integrates directly into local applications, it has its own in-app browser for web development, and it connects to remote DevBox environments.
Wait, so it is actually clicking around and using the computer?
Yeah, actually. It is conducting full pull request reviews on its own. It is performing the actions of a developer, not just generating text.
That is full on. And what about Anthropic? Are they pushing the same boundaries with Claude Opus 4.7?
They are, particularly with high-resolution vision and multimodal support. That allows the model to process complex visual system architectures perfectly.
Okay, so it can actually look at a system diagram and understand it.
Spot on. But what tells you everything you need to know about the current state of artificial intelligence is actually what Anthropic chose to hold back.
Oh, really? What did they hold back?
They deliberately restricted the cyber capabilities of Opus 4.7. They integrated strict new cyber safeguards and a verification program, so they kept it intentionally less advanced than their internal Mythos preview model.
Wow. So they are holding it back because they know exactly what happens when these models operate without constraints.
Exactly. They know the risks.
I was reading through the materials, and there is a fascinating example of researchers pointing Codex at hardware. They gave the model a browser shell, which is basically just a tiny foot in the door, and the firmware source code for a Samsung Smart TV.
And their only instruction to the model was to find a vulnerability and get root access.
So they just pointed it at a television and said, go hack this.
That was the entire prompt, yeah. And Codex just hunted through the firmware. It located an unknown critical flaw in a kernel driver called intrusis, and then executed an incredibly sophisticated exploit.
Just off that one prompt.
Yep. It figured out how to map arbitrary physical memory directly into user space, and that allowed it to overwrite the browser process kernel credentials.
And that gave it control?
With those credentials overwritten, yeah, it gained full root access to the device.
Okay, you need to break that down for me, because that sounds like pure hacker jargon. What does mapping physical memory into user space actually mean in plain English?
Sure. Think of a computer operating system like a highly secure bank. The user applications, like your web browser or a streaming app, are the regular customer standing in the public lobby.
Okay, I'm with you.
The kernel is the bank vault, where all the core rules and deepest security secrets are kept. Customers are never allowed in the vault.
Right. Makes sense.
What Codex did was find a tiny architectural flaw in the bank blueprints. It used that flaw to build a secret tunnel from the public lobby straight into the vault.
Oh, wow.
And then it simply rewrote the bank manager ledger to make itself the new owner of the bank.
It is like handing a highly caffeinated toddler a lockpick set and just hoping they fix the squeaky door hinge.
That is a great way to put it.
Which, yeah, is exactly as terrifying as it sounds. But if an AI can build a secret tunnel into the core memory of a device, are we fundamentally misunderstanding what these things are?
I reckon we are.
I mean, if they are finding kernel driver vulnerabilities and executing complex memory exploits, they are not autocomplete scripts. They are full-blown hackers.
We are definitely misunderstanding them. When a system can read firmware, identify a zero-day vulnerability, and chain complex exploits together to escalate its own privileges, it is an active operator.
It is actively participating.
Right. It deeply understands underlying system mechanics. And treating an active operator like a glorified spell checker is incredibly dangerous.
So how do we even handle that?
It requires entirely new security postures. You cannot just review the code it writes. You have to constantly monitor the physical access it holds across your network.
That makes total sense. So if the raw capability allows them to own a smart television, what happens when you let these hyper-capable entities live permanently inside a massive, messy enterprise code base?
That is where it gets properly weird.
Because if you have ever tried to debug a monolith, you know how painful it is. It is a giant, tangled ball of yarn where changing one file inexplicably breaks 50 others. How are companies safely deploying them there?
Well, we are seeing tech giants deploy these agents to perform massive structural changes across their entire architecture. Meta, for example, built unified AI optimization agents.
Okay, what do those do?
These are not writing shiny new features for users. They are actively hunting down and fixing performance regressions across the Meta hyperscale infrastructure.
But how does an AI know what constitutes a performance regression in an infrastructure as complex as Meta? That sounds impossible.
Meta gives the AI access to the exact same shared tooling a human engineer uses.
Oh, I see.
The AI can pull profiling data to see CPU usage and memory leaks. It can use code search functionality, and it can review configuration history.
So it has all the standard tools.
Yes, but the crucial step is that Meta took the domain-specific logic and the investigative workflows used by their most senior staff engineers, and they encoded those directly into the AI prompts and skills.
Wait, so they effectively downloaded the troubleshooting brain of a senior staff engineer and plugged it directly into their profiling tools?
That is exactly the mechanism.
Yeah.
That is brilliant. Because the AI processes that profiling data instantly and applies the senior engineer logic, it can take a performance degradation issue that normally requires 10 hours of manual investigation by a human and compress that entire investigative loop into just 30 minutes.
Just 30 minutes. That is unreal.
It traces the complex dependencies and auto-generates the final pull request to fix the issue.
That is massive for fixing bugs. But I want to look at Monday.com, because what they did with their AI agent, Morphex, is just wild.
Oh, the Morphex project is fascinating.
They built Morphex using the Claude Code SDK and essentially let it spend a massive chunk of time decomposing their production monolith unsupervised.
Yeah, the Morphex project is a perfect case study in how autonomous agents evolve in production. Over that period, Morphex opened thousands of pull requests, and it auto-merged those changes through continuous integration.
Just for the listener who might not be deep in DevOps, continuous integration just means the code is automatically tested and merged into the live project without a human manually clicking approve every single time, right?
Correct. The system runs automated tests, and if they pass, the code goes live.
Simple enough.
But the really fascinating part of the Morphex experiment is how the AI improved its own approach over time. It started by making very simple mechanical file moves, just reorganizing directories.
Easy stuff.
Right, but eventually it began executing complex architectural reasoning.
Okay, what does complex architectural reasoning actually look like for an AI?
It means the AI started understanding the hidden relationships within that tangled ball of yarn. If it wanted to move a specific database function to a new service, it knew it also had to update the authentication module and rewrite the API endpoint.
All on its own.
All without breaking the live application. It understood the blast radius of its own code changes.
It is like a digital termite that only eats rotten wood. It just slowly digests the bad legacy code while leaving the load-bearing architecture perfectly intact.
That is a brilliant analogy.
But hang on. If it's making thousands of architectural changes, how do the human engineers possibly keep up?
Well, that was the biggest takeaway from the Monday.com team. The hardest part of the project was not building the AI.
The AI was the easy bit.
Exactly. The AI was highly capable. The real challenge was building the organizational guardrails to support an autonomous worker.
What kind of guardrails?
They had to invent rigorous new validation checks, establish clear accountability transfers for when the agent inevitably breaks something, and design entirely new triage systems just to safely absorb that massive volume of automated change.
Honestly, building triage systems for an AI employee sounds exactly like middle management.
Huh.
Because apparently that is where we are now. We are just managing the AI middle managers.
Yeah, it highlights the ultimate coordination problem. If you have multiple AI middle managers running around opening thousands of pull requests simultaneously, how do you stop them from stepping on each other's toes?
Right.
Or even worse, how do you stop them from just forgetting what they were doing mid-task? Because language models have a context window. Eventually, the early instructions just fall out of their memory.
See, I genuinely assume that as we get smarter models with massive million token context windows, the AI would eventually just hold the entire project in its head. Why does throwing more compute at the problem not solve that coordination issue?
Because multi-agentic software development is not actually an AI problem. It is fundamentally a distributed systems problem.
Wait, really?
Yeah. And computer science is bound by mathematical limits. There are inherent impossibility results in distributed systems, like the Byzantine generals problem, or classic theorems like FLP.
Right.
You cannot fix a distributed systems problem just by making a language model smarter.
Okay, you are going to have to unpack the FLP impossibility theorem for me. Why does it matter here?
To understand it, think about the Byzantine generals problem first. Imagine several generals surrounding a city. They need to attack at the exact same time to win. If they attack at different times, they lose.
Got it. High-stakes coordination.
Right. They can only communicate by sending messengers, but those messengers might get captured or delayed. How do they guarantee they all agree on the plan?
They cannot be certain.
Exactly. The mathematics prove that in a purely asynchronous network where messages can be delayed, reaching perfect consensus is extremely difficult. The FLP theorem takes this further.
It proves that in an asynchronous network, if even one single node might fail or delay its response, you cannot guarantee that the overall system will ever reach an agreement.
So if Agent A is waiting for Agent B to finish rewriting the database, but Agent B hallucinates and gets stuck in an infinite loop, the whole system just freezes.
It deadlocks completely, yes.
Wow.
You can have the most advanced artificial intelligence in the world, but if multiple agents are working without explicit, rigorous coordination protocols, they will eventually overwrite each other or freeze. You cannot outsmart fundamental mathematics.
I am genuinely surprised by that. We are pushing the absolute boundaries of artificial intelligence, but we are still shackled by decades-old computer science proofs. How are engineering teams getting around that?
Well, we can look at how Slack engineering tackled this exact limitation for their long-running security investigations.
Oh yeah, I saw this in our materials.
They realized a massive context window was not enough, so they built 3 complementary context channels to force their agents to coordinate and bypass those memory limits.
They built a system with a director's journal, a critic's review, and a critic's timeline. How did those 3 channels actually interact to stop the deadlock?
They separate the cognitive load. The director's journal acts as structured, immutable memory. It records the overarching goal and the current state of the investigation, so the AI never forgets its primary mission.
That makes sense. Keep the main thing the main thing.
Exactly. Then you have the critic's review. This channel acts as an aggressive filter. It evaluates the findings of the other agents and actively prunes away hallucinations or irrelevant data before it pollutes the main workspace.
Like a dedicated fact checker.
Right. Finally, the critic's timeline constructs a chronological, logical sequence of events to ensure the investigation actually makes sense in the real world.
That setup is brilliant. It sounds exactly like a true crime audio production team. You have the director taking structured notes, making sure everyone is focused. You have the grumpy fact checker tearing apart all the wild hallucinated theories. And then you have the timeline builder standing in the corner, pinning red yarn on a corkboard to make sure the sequence of events lines up perfectly.
That is an incredibly accurate way to visualize the architecture. By forcing the AI agents to communicate through those strict separate channels, Slack bypassed the limits of the context window.
That is so clever.
They created a system that can run indefinitely without collapsing under its own weight or deadlocking.
But even if we have a perfectly coordinated true crime AI team, they are still generating massive amounts of code. How do we enforce physical constraints on the code itself?
That is the next big hurdle.
Because if we just trust them, we are going to end up with repositories full of vulnerable, vibe-coded garbage.
We have to move away from hoping the AI does the right thing and start forcing it to do the right thing at the compiler level.
So making it structural.
Exactly. There is a movement gaining traction right now summarized in the AI Coding Agent Manifesto. It establishes new rules for AI-driven development.
What are the core rules?
The core argument is that humans must define the code skeletons, and we have to treat all AI-generated code as guilty until proven innocent.
That guilty until proven innocent mindset completely changes the architecture. It leads to the principle of prioritizing contracts over conventions, right?
Yes, spot on. A convention is asking the AI nicely, please format user data this way. A contract is a physical barrier that breaks the code if the AI disobeys.
Give me a practical example of that.
A highly practical application is the philosophy that everything should be typed. In standard programming, you often use generic scalar types like strings of text or integers.
Right, pretty standard stuff.
But relying on strings is incredibly dangerous when an autonomous agent is writing the code, because strings hide subtle semantic bugs.
How does a generic string hide a bug from the developer?
Imagine you have a function that sends a highly secure financial document. It requires two inputs, a customer ID and an account ID. Both of those inputs are formatted as strings of text.
Okay, I am tracking.
If the AI agent hallucinates and accidentally swaps them around, putting the account ID where the customer ID should be, the compiler checks the code and says, well, the function asked for a string and you gave me a string. Everything is perfectly fine.
Oh, I see.
The code compiles without a single error, but when you push it to production, the system crashes, or worse, sends the financial document to the wrong person.
Because the compiler cannot tell the difference between the two business concepts. It just sees the underlying data type.
Precisely. The solution is to wrap every single meaningful domain concept in a distinct new type. You do not pass a generic string. You explicitly define a customer ID type and an account ID type.
So you separate them completely.
Yes. When you do that, the compiler itself enforces the semantic correctness. If the AI hallucinates and swaps them, the code physically will not compile. The type system becomes a concrete wall the AI cannot bypass.
I am going to push back on that, though. Writing a custom type definition for every single concept in a massive enterprise system sounds exhausting.
It sounds like a lot of work.
Does wrapping every domain concept in a strict new type slow down human developers so much that it completely wipes out the speed boost of using the AI in the first place?
It is a common hesitation, but the reality is the exact opposite. Strict types actually liberate the human developer.
How so?
Yes, you spend a little extra time defining the structure up front. But think about the code review process. If you use generic strings, a human has to manually read every single line the AI generates to make sure it did not swap two variables.
Which would take forever.
It causes immense review fatigue. When you use strict types, the compiler does that heavy lifting for you. You catch the AI hallucination instantly at compile time, instead of weeks later during a production outage. It dramatically accelerates the overall development loop.
So you put up the concrete wall so you do not have to watch the digital termite every single second. But hang on, even if we use strict typing to stop the AI from making internal logic errors, we do not write all our code from scratch. We pull in external libraries.
Of ways.
If our AI decides to download a malicious package from the internet to solve a problem, all our internal typing is completely useless. How do we defend the supply chain against an AI that just wants to download a quick fix?
Supply chain defense is critical, because historical data shows the majority of attacks on package managers like NPM are essentially smash and grab jobs.
Smash and grab, meaning an attacker uploads a malicious package, waits for people or AI agents to download it, and then the package gets flagged by security researchers and yanked down a few hours later.
Exactly. And researchers have found that the most effective defense against this is not some highly advanced AI analysis tool. It is an incredibly simple procedural delay.
Just a delay.
Yep. You set a rule in your system called minimum release age equals 7 days. That is it. If an external package has not been public and available for at least a week, your system simply refuses to let the AI download it.
And researchers looked at major NPM supply chain attacks over several years.
I did.
They found that this one simple delay tactic would have successfully blocked 11 out of 21 major smash and grab attacks.
It forces the AI to use mature, vetted code. It is a fantastic example of how sometimes the best way to manage highly complex, fast-moving autonomous systems is to introduce deliberate, immovable friction.
Deliberate friction. I love that. So we started by imagining a junior developer with root access tearing apart our monolith.
We certainly did.
And now we are talking about digital termites digesting legacy code, true crime audio teams pinning red yarn to corkboards to solve distributed systems problems, and deliberately slowing down our package managers to stop smash and grab attacks.
It is a lot to take in.
It really is. And it leaves me with a massive thought to chew on. As these capabilities keep accelerating, are we actually still building tools to write code? Or are we fundamentally shifting into building entire digital ecosystems just to manage the autonomous workers doing the building for us? It completely redefines what it means to be an engineer. Keep exploring these ideas and try to keep your AI middle managers online before our next session of Vocal Technologist.
Spoken Tech for your ears.